All right, so this video is going to describe some basic properties and approaches to triangulation. Um, I'm basically using triangulation in a Bluetooth design setup where I have two beacons that receive Bluetooth signals that can then triangulate the position of some Bluetooth device. So I use Desmos because it's amazing and it can be used to describe this approach. So imagine you had a user um, moving around this plane, right? We kind of have a bird's eye view, um, and then we have the XY plane that represents a position. Beacon one, I just conveniently put on the origin, and then another beacon at 2, 2. So if I was to move this user around, it's going to be sending signals to both beacon 1 and beacon 2, which then beacon 1 and beacon 2 will approximate the distance that the user, where the user is located. So if I was to put the user in any position and then ask beacon 1 to describe the location, it would give me a radial distance, right? It can tell me the distance of the object as a radius of a circle, but not the position, right? So independent of where I put the user, it can define a particular distance that the user is to the beacon one. And then if I was to ask beacon two would also respond with a distance, right? But the magic of this is that the intersection of these two circles would represent the location of the user. Now, the problem with using only two beacons is that in every situation except for a line location that is tangent to a straight line going through beacon one and beacon two, there's going to be two solutions, right? So it's possible that the user is here because it would meet the situation where it was this distance from beacon two and this distance from beacon one, or it could also be here where it's this distance from beacon one and this distance from beacon two. And later I will describe an alternative approach I took that pretty much solves this problem. So how would you solve this equation? Well, the approach I took was, well, let's see, what do we know? Well, we know the distance between beacon 1 and beacon 2. That is fixed, right? So this distance between beacon 1 and beacon 2 can't change, right? I put beacon 2 in a certain location, I mark it. I put beacon 1 in a certain location, and I mark it. All right. Also, the distance from beacon 1. I don't know where it's located, but I know the radial distance. Same from beacon 2. I know the distance from beacon 2 and a radial distance. So what does that tell me? Well, it gives me a triangle. And I'm going to remove these two lines so you see a triangle that tells you the position of any object. And that's where the term triangulation comes from. So to solve this, you would use the law of cosines because I know a side, and a side. So side, side, side. I could find this angle and then use polar coordinates to get the distance, distance and an angle. And then it would actually give you the orientation as though this blue line was on the x-axis. So then you would have to do a rotation to get it to the right position. So this is one approach, but like I mentioned before, the issue is that it gives you two solutions. So what is a better approach? Well, the better approach I created was a 3 beacon approach. So imagine you had a device, say same situation as before, and the XY plane is the floor, and we have a bird's eye view. How would we find this device? Well, let's just ask the beacons again. So this beacon 1, is giving me this distance away, right? This radial distance. I ask beacon 2, and beacon 2 gives me this radial distance. Now, again, this is very similar to our last solution where we have two intersections. But then if I introduce a 3rd beacon, there is only one place where all 3 circles intersect. So that gives you one solution. Well, you could possibly use a triangle to solve this, where you would have to ask 2 circles, find a triangle, and find the 2 solutions. Then use 2 other circles, make a triangle, find 2 solutions, and then find the solutions that are the same. And I suppose that would work. Something that I figured out, which works even better, is to just take these three equations, put them in a linear system, FOIL these out, um, subtract this solution from this solution, and subtract this solution from the third solution, and you will get these two linear equations. And these two linear equations are just two straight lines, and we know using linear algebra, it's really easy to solve, you know, two straight lines and find where they intersect. Just set them equal to each other. Um, and yeah, that's pretty much the approach I use to triangulate the position of any object. This is only a two-dimensional representation, right? I don't have, I'm not using spheres to represent the beacon's ability to find real distances. This is just a flat two-dimensional circle. And yeah, that's it. Thank you.